Okay, so we're going to be starting chapter 12, and chapter 12 is called Stoichiometry. And if you have heard anything about chemistry before taking this class, stoichiometry may have been something you've heard about. Now, some people, I think, over exaggerate a little bit how difficult it can be. And it's definitely not something to be afraid of. It's definitely something that we can handle. It is a little bit mathy, but that's okay. Sometimes we need to just work on those math skills. It really isn't anything new from what we've been doing as far as just converting things from grams to moles or moles to grams. We're just basing things off of a chemical reaction. So we're given like a specific situation and we have to use some things based on what the equation tells us. So we'll be setting our problems up much in the same way as chapter 11. We're just going to use information from a specific chemical equation. So what is stoichiometry? The formal definition of stoichiometry is a series of unit conversions that convert from one quantity to another based on a certain chemical reaction. So anytime we do something in the lab, we're using stoichiometry. Every time a chemical something happens and we get a reaction, that's stoichiometry. Everything has to react in a certain type of balance in order to react effectively. Now, sometimes in nature we might have things that don't react perfectly, and that means the stoichiometry is a little bit off. Maybe I don't have enough of a certain element, or I have too much of something and not enough of another, and that can throw off what product I get or how much product I might get from a reaction. Stoichiometry is basically representing the ideal or perfect situation. So if you have an exact amount of various substances, you will produce exactly this amount. So it gives you kind of the ideal situation, and sometimes that does happen. But again, science and the world as we know it is a little bit unpredictable, so that's not always the case. So to make different things that you're familiar with, for example, I just found this diagram, gasoline and toothpaste, a little bit of a weird combination of things to analyze with, but I like the graphic and I like the captions. So anytime you have a mixture of something, that's taking advantage of stoichiometry. So it's taking advantage of, reacting some different things in a certain ratio to get a certain product. And that's how we have a lot of the products that we get today. Toothpaste, gasoline, what have you, anything that you have to react something with to get a product, that's going to take advantage of stoichiometry. So, whenever we have a chemical reaction, of course, we can't create more than we start with, so we have to make sure we follow the conservation of mass. And if you remember back from chapter 10 when we started talking about chemical reactions, we talked about balancing chemical equations, and when we balance chemical equations, it follows the law of conservation of mass. It preserves that. It shows that we have an equal number of products and an equal number of reactants. Now, what else does this mean? Well, let's think about it. I know I have to have, when we balanced equations, we made sure we had an equal number of each element on each side of the equation for each of the specific elements that were listed. And what I know now is that each element has a certain mass, a molar mass, that I can calculate from the periodic table. So if there's equal amounts of elements on both sides of an equation, then there's got to be an equal amount of that mass as well. So obviously the mass on the reactant side always should equal the mass on the product side. Now, when we want to do use chemical equations to do stoichiometry type problems, a lot of times we'll convert moles of a compound into grams. That's usually our main conversion. And sometimes we will start with moles of something and convert to moles of another thing, so kind of one-step problems. We might take it a little further, do moles to grams, and we might take it a step further and do grams to grams. So it just kind of depends on what we're given, but the whole time we're going to be following the law of conservation of mass. Have to. So this is stoichiometry. Let's go ahead and look at one of the most important parts of stoichiometry, and that is this, mole ratios. So whenever I look at a problem, sometimes I might give you the chemical reaction, other times I might have you write out the reaction. So if you're writing out the chemical reaction, you want to make sure you're feeling good about writing formulas from names again. So if that's something you need to go back and touch on, or if you'd like any of the old handouts, if you've misplaced some of those from last semester, or recycled some of those that I know some of you probably have. If you need another copy of those, I can get that for you. Just make sure you ask me. Sulfur dioxide gas here reacts with oxygen and water to produce sulfuric acid. So the first thing you want to make sure that you do is you write the chemical reaction. And I'll get to this stuff down here in a minute. Sulfur dioxide, so that means I have one sulfur and two oxygens, and that's a gas, reacts with oxygen, which is typically a gas. And remember, oxygen is one of those things that's diatomic, so whenever I record oxygen, I always have to record O2. And then it says it reacts with water, so water is H2O. And then we have sulfuric acid. And with our acid naming, we had two types. We had certain acids that said hydro in the front, and we had other acids, like this one, for example, that did not have the hydro prefix. If you did not have the hydro prefix, those compounds, that meant that that acid had to contain oxygen. So that's where you kind of want to remember your polyatomic stuff. Sure, I'm getting lots of evil stares through the computer here, but yes, our polyatomic things, we need to make sure we remember those. Sulfuric acid, sulfuric, sounds like sulfate. So your equation should look like this. Sulfate is SO4 minus 2, so and hydrogen is always a plus 1, and acids were a thing that we crisscrossed. So we should have 2 hydrogens and 1 sulfate. Now, I've already gone and went ahead and balanced this equation. Now that's something that you would want to do if I give you a problem. You always want to make sure you're working with a balanced equation in stoichiometry. If you're not really doing stoichiometry. Stoichiometry relies entirely on the fact that you have a reaction, it's balanced, you know the exact amounts that need to react, and all the while you're following the law of conservation of mass. So, here, let's look at our equation. Like I said up top, the most important thing in stoichiometry, besides having a balanced equation, is to know what mole ratios you've got. So let's talk a little bit about that. Here I have a 2 in front, so that means I have 2 sulfur dioxides. Now, when we're doing chemical reactions, there's, yes, individual elements reacting, but for the sake of measuring things out in the lab, I can't measure out one atom or, two little units for a compound at a time. It would be so small, I wouldn't be able to see it. So in the lab, we have to work at least in, a certain mole quantity of something. I have to have it, close to 6.02 times 10 to the 23 pieces, just so I can see things and just so I can work with things. So what we assume with our reactions is that we have 1 mole of our substances, and then we go ahead and balance that to make sure everything's equal. So that these numbers now mean how many moles of a certain compound you've got. So here, for example, I have 2 moles of sulfur dioxide, 1 mole of oxygen. If there's nothing written in front, we can still assume it's 1, that's fine, plus 2 moles of H2O, or water, yields or produces 2 moles of H2SO4. So now we kind of want to think about, I have to work with this stuff in the lab, I have to see it, so I need to make sure I have enough, or I'm representing enough pieces so I can see the stuff. So think of these numbers in front now representing the number of moles of that thing, that compound. So when we're doing stoichiometry, we will use these mole ratios. So basically, if I want to convert, let's just say, if I start with sulfur dioxide maybe, and I have 30 grams of it, and I want to figure out how much sulfuric acid that would produce, or H2SO4, I would do a series of conversion steps, and I'd have to know, based on the chemical equation, well, what's what's the recipe here? So I know I have to have 2 sulfur dioxides for every 2 H2SO4s, because that's the balanced equation. So these little things or coefficients in front you can also think of as kind of like your chemical recipe. This is how much of one thing you need in order to produce or react this much of another. So here's where our mole ratios come in, and these will be used in our conversions a lot of the time because it kind of just lets us know what the recipe is and how the two things are related based on our equation. So if I give you an equation or I have you write a reaction out, I'm going to ask you to find all of the possible mole ratios, or as many as you can. I might say find 5, find 6, or find them all. In this case, I think I found most of them. I may have missed a couple, but the process is pretty much the same. It's just making sure you get all the combinations. So if I want to write out the mole ratios, I'm just finding and comparing one compound to another, and I'm basically just representing how many of each there are. So I'm looking at the coefficients in front. So here, if I want to start with, I always start with the first thing listed and I compare it to the second thing that's listed, and I just keep going down the list. So here I have 2 moles of sulfur dioxide plus 1 mole of oxygen, and I can represent that in a mole ratio, and I've written that here. So I'm comparing 2 moles of SO2 over 1 mole of O2. That's a mole ratio. There's moles on top, moles on the bottom, and the numbers that represent how many of those that there need to be. Now I can flip that around because I can take a fraction and flip it mathematically. So I can also say, well, I have 1 mole of O2 or 1 mole of oxygen for every 2 moles of SO2 or sulfur dioxide. And I can go through this whole equation or this whole recipe, and I can compare all those compounds to each other based on the number of moles that are there. So you can kind of think about moles as the middle ground in stoichiometry. That's kind of the unit where we're kind of all equal, so to speak, as far as the number of things, or we know we're representing a number of pieces when we say moles. So again, I can kind of go through and I go through and I compare. So I start with the first compound, I compared it to the second one, write the ratio, flip the ratio. Okay, that takes care of that combination. Then I look at the first one, and if there's a second or a third reactant, I compare those two together. So I have 2 moles of SO2 and for every 2 moles of H2O. And then I can flip that fraction, so I did that over here. So 2 moles of H2O for every 2 moles of SO2. And then I can just keep going. So I can compare, obviously, the SO2 to the sulfuric acid, and I just keep going through and I write those ratios over each other, and then I can flip them. And that's what the equation tells me. This is kind of the main part of stoichiometry, is being able to read your recipe and know what you're getting out of it. So it's kind of like if I'm going to bake a cake and I want to double the recipe or maybe triple the recipe, I know I have to triple all of the ingredients, but those ingredients are always kind of set in a certain ratio. So I might, for every 2 eggs I throw into the batter, I might have to have a cup of milk, something like that. So those are like the recipes and the quantities and the ratio of the things that I need in order to bake a good cake. In order to have an effective reaction, you have to make sure the equation's balanced and you have the right mole amounts for everything. You have the right recipe or combination. So for your homework tonight, there's just a little worksheet where you're just writing out an equation, or I'm giving you an equation and you're writing out the mole ratios. And there's also a few questions about the video on there, so if you need to rewatch or kind of look back through your notes, that's perfectly fine. But this just kind of gives you a basis and kind of leads into what we'll talk about tomorrow, and we'll actually practice doing some conversions tomorrow with stoichiometry and get some good practice with that. So make sure you have your notes. There will be an open note quiz about this tomorrow, so be ready for that, and I will see you then.